In this next section, we are going to look at the definite integral. The definite integral can be broken up into three different representations, and so we're going to first talk about the numerical methods behind integration, the definite integral. The definite integral is going to be denoted very similarly to our integral or antiderivative. The main difference is now we're going to have some limits on the integral notation. Okay? This is a real number, so once we calculate it, unlike the indefinite integral or the antiderivative, we aren't just getting a function. So remember, in those cases, we're getting some f of x plus c. Here, we're actually going to come up with a number. And in some cases, that number is going to represent the area under the curve of our function over some interval. Okay? And so pictorially, if I have some function f of x that looks like this, there's a generic function, and I have some interval from a to b, then the definite integral is basically giving me the area bounded by the x-axis for the region under that curve. And the reason I say it's for specific cases is because if my function f is not entirely above the x-axis on that interval, or it has, if there's more than one function that I'm looking at, so maybe there's an f and a g, it's going to take a little bit more to figure out what the area is going to involve. Okay. So as I mentioned, we're going to look at some numeric methods. Now, before we get into this, there are many numerical methods for solving integration problems. For us, we are only going to consider one of those methods, and that's the method of Riemann sums. Okay? So for most geometric figures, so if I think circles, squares, rectangles, triangles, those nice geometric figures, we have formulas for finding the area. Okay? For curves, so generic functions f of x, we can approximate the area using these Riemann sums. Okay? And Riemann sums basically use rectangles, which we know the formula for to find the area, to approximate areas of subintervals under a curve. Okay? And to make that more clear, I have a couple examples here. We're going to take a really nice function. So obviously all of our functions are not going to be this nice, but we're going to start with these just so you can get the idea of what we're talking about. And as we move forward with these, we'll get into some of the other methods that relate to these numeric methods. Okay? So in this picture, I've got a function f of x equaling x plus 1 on an interval from 0 to 4. And for this one, I'm going to use 4 subintervals in my Riemann sum. Now, when I look at the Riemann sum, there are two ways I can approximate the Riemann sum. There's what we call left-hand Riemann sums and right-hand Riemann sums. Okay? For this one, I'm going to do both. So with 4 subintervals, I'm going to start with the left-hand side. And so I'm going to basically take my interval from 0 to 4 and break it up into 4 subintervals and look at the left-hand endpoints. Okay? So here, if I look at the left sides, or my 4 subintervals, I can basically take and divide this just on the integer values between 0 and 4. And that's going to give me my 4 regions, or 4 subintervals. Okay? And if I approximate this using left Riemann sums, I can see that my rectangles are going to take the height of the function at the left-hand endpoint. So in this case, I'm looking at 0, 1, 2, and 3 as my left-hand endpoints. And if I look at those rectangles, there's what my rectangles would look like. Okay? And so to get my area from this, it just says I'm going to use my formulas for areas of rectangles, which is basically the length times the height, or the length times the width, if you think of them kind of sideways. So for each one, I can see the length is going to be 1 unit, and the height is going to be the height of the function at that left-hand endpoint. So at 0, my function value is 1. At 1, I can see my function value is going to be 2. At 2, my function value is going to be 3. and at 3 my function value will be 4. Obviously my picture is not drawn to scale, so bear with me. Okay, and then I'm just going to add these up. But what I'm going to do before I add them is I want you to notice something, because this is going to be important when we get to our algebraic method. When we get to the end of this numeric method. One of the things to notice is if I write it out like this, the length times the height for each of these intervals, I notice that each of the lengths is exactly the same. So I can factor that out front and then just add up the heights. Okay? And so in this case, my left Riemann sum is going to have a total of 7, 8, 9, 10 times 1 or 10. That would be an approximation to my area using the left-hand endpoints of this particular interval. Okay. Now, like I said, we're going to do both left and right. So if I look at the right-hand endpoints, or the right Riemann sum, the only thing that changes is what I'm going to use as my heights. So I'm still going to have the same subintervals. Okay, I'm going to kind of draw them sideways there, on there. Okay, so the same 4 regions. The difference is now I'm looking at 1, 2, 3, and 4 as my right-hand endpoints. And so when I take my height of the function, so again, at my first one, the length is still going to be 1, but now I'm taking the height, I know that's not straight, but I'm taking the height there. So at 1, I have a height of 2. At the next one, when I come over, I'm getting a height of 3. At the next one, I have my height of 4. And at my last one, which is the value at 4, I have a height of 5. Okay. And same thing. I can factor out that length. That's the same for all of them. And then add up the heights. And so what do these numbers mean? So as I've said before, I kind of drew those lines all the way out there, but basically what we're looking at is these rectangles. Okay. So what we're looking at is the blue here is giving us an under approximation of our height, and the purplish red is giving us an over approximation of our height. And so one of the things to notice is if I increase the number of subintervals, the better the approximation is going to be. Okay? And that may not be apparent just yet, so I'm going to look at this one more time. Let's look at that same function on the same interval, but now let's look at 8 subintervals. Okay? So if I do the same thing, my left Riemann sum says I'm going to take this and I'm going to divide this into 8 subintervals. Okay, and I'm going to use the left-hand endpoints. Short. Okay, and so one of the things you can see is, well, obviously there's more rectangles that we're looking at, but if I look at the difference between the kind of open spaces between my curve and the rectangles, they're a lot less over here. Okay, and so again, in this case, I know my width of my interval for all of these is going to be 1/2. Right, so from 0 to a half to 1, 1 to a half, 3 1/2, etc. And then I just need my height of the function at each of the sub-endpoints. Okay, so again I'm starting at 0, so I'll be at 1. At a half, I'll be at 3/2. At 1, I'll be at 2. And I can keep going up until I have my 8 points. Okay, and we can see the next one would give me a value of 5, which would mean I'm at the 4, but that's the right-hand endpoint. Okay, so same thing, I'm going to go ahead and add this all up. So we'll get 3, 6, 10, plus 8, 15, 24 over 2, which looks like 12 and 10 is 22. So there's my left Riemann sum. And again, notice I didn't quite get the same thing I got here because my area is filling out more of the region. Okay. So likewise with the right Riemann sum, I'm going to see something similar, except again it's going to be an over approximation to the area. So with the right, we can see here when I do my rectangles, I'm going to get slight over approximations. Okay. And again, here where I had really big spaces between my rectangles and my curve, we can see they're a lot smaller. There's more of them, but they're smaller. Okay. So same thing. I'll take my width for all of these, which again is going to be a half. But now I'm going to use the right-hand endpoints to get the height of the function at each subinterval. And I can see that my heights here are going to start at 1/2. So I'm going to start at 3/2 for the heights. When x is a half, I get 3/2 in the function. Then at the next point, and so forth, all the way out to my last right-hand endpoint. Okay. Same thing, I'm going to go ahead and add all of these up. So we can see for the halves, I'm still going to get 24 over 2, but for these, I'm going to get 10, 14, 15, 14, 17, 18, 19. Okay, so 12 and 19 looks like a 31 over 2, which is about 15 and a half. Okay, so to continue with our numeric methods, we mentioned using the Riemann sums to find our area. And as we saw in the last example, as our n increased, so the number of subintervals increased, the approximations got a little better, meaning the rectangles got closer and closer to our curve. And so ideally, if we want to get an accurate area for this, we want our number of subintervals to be as large as possible so that the width on each of those is as small as possible. Okay? So using the Riemann sums, if the number of subintervals increases, obviously the approximation gets better. So what we want is we want our definite integral to be a sum of the heights times the widths, where we add all of those up, but we want the number of subintervals to go to infinity. And so we're going to end up taking a limit. Again, here n is the number of subintervals, delta x is the width of each subinterval, and f of x sub I is the height of the function taken in the ith subinterval. Now here there's a caveat we've got to mention, and that is, in the last example we looked at left-hand and right-hand Riemann sums. But the idea is, as I get more subintervals and my intervals get smaller, it really isn't going to make a difference what point I pick in the interval, whether it's the left hand, the right hand, some midpoint, or any other point in between. So as my n goes to infinity, Here I just need to find a point in the interval and use that to find my height. Okay. So one thing we're going to need before we can actually look at these limits is we're going to need to remember some summation formulas. So if you don't remember these, that's okay. These are the ones that we're going to use most often in these types of problems. And so the first summation formula to remember is, if I am looking at a summation, first off, I here is what we call our index. This is the variable of our summation. So anytime I see an I, I'm going to replace it with the numbers from 1 to whatever that n value is. And in this case, that n value is the letter n, or the arbitrary number n. And I'm going to sum those all up for whatever the function is. In this case, my function is k. K is just not I, so k is some constant in terms of I. And if I have a constant in terms of I, that just means I'm going to take k and I'm going to add it to itself n times. Okay? So there would be my formula. For the I, if I'm actually looking at the variable and I'm just adding that variable up, so from 1 to n, this would be like 1 plus 2 plus 3 plus 4 all the way up to n. This is just going to be n times n minus 1 all over 2. That's plus.